My name is Natalie and I'm a nerd research fellow at the University of Cambridge. Today I'm at the Royal Society Summer Science Exhibition because together with my colleagues from the University of Sheffield, Chris Keylock, and University College London, that's Paul Brennan, we're presenting a display on snow avalanches, setting a speed trap for an avalanche.
How did you get interested in avalanches then?
I used to do research for my PhD on sand dunes in the desert, in the Mojave Desert in the United States. These, you may think, well, what's the overlap between sand and snow? But both are composed of particles, and these particles are moving along each other, they're bouncing, colliding, and sliding. So, in principle, sand and snow is not that different. So I used to work in the heat of the desert, but I moved to the cold of the mountains to do snow avalanche research.
So there's two halves of the exhibit. One is about granular flows, so flows which have particles in, and the other side is the radar half. So we've got this little stand that has lots of hundreds and thousands, which all have roughly the same density. And what you can do is mix everything up so that everything is just kind of randomly arranged. And this is like your snowpack before the avalanche happens. Then we can deliberately start an avalanche. If you look down the side, you can see that all the big particles have started to come to the top. And that's because the small particles can form in the gaps between the large particles. The same thing happens with snow as it flows down the side of a mountain. So around the front and around the edge, and you get these large blocks of snow, and the smaller, finer snow gets stuck in the middle. So by doing these small kind of laboratory experiments, we can understand some of the physics of what's going on when avalanches flow down the slope. So we have a radar which is on one side of a valley, looking across the valley, and then we set off avalanches by explosives, so usually from a helicopter to try and prevent disasters. And then we record the course of an avalanche. So the principle is much like a police radar gun. So what the police do is they send out a beam of radio waves at someone they think is speeding at some frequency they know. When it gets reflected back, that frequency is changed or modulated depending on the speed at which the car is approaching. And in much the same way, as radar waves which get sent off towards the avalanche at some frequency we know, get reflected back by the moving avalanche, and so we can back out from the data we receive from that how fast the avalanche is moving at every second. The great advantage, we can not just see the kind of big clouds of snow and stuff which are chucked up into the atmosphere when the avalanche is flowing. We can also see the dense core of the snow, which is the kind of the heart of the avalanche and where all the destructive power is.
Now, once the avalanche is already in motion, isn't it too late to do anything useful?
You're right, at that moment the avalanche is already in motion and it would be very hard for people to move out of the way because avalanches travel really fast. They travel up to 100 miles an hour or 160 kilometers per hour. So that's not the direct application. We're more interested in measuring large-scale avalanches in Switzerland and getting parameters from that to put in our mathematical models. Next, we're using these mathematical models to calculate whether the avalanche defenses that are being designed and built are strong enough and high enough to actually protect the people that live behind them in the mountainous communities.